From any vantage point, the cosmos looks fundamentally the same. This cosmic sameness is one of science's deepest puzzles. By the end of this journey, you will understand the violent origins of our uniform reality. We will explore how the entire observable universe could have agreed on its rules without ever communicating, and what a period of faster-than-light expansion has to do with the stars you see tonight. What does it mean to you that the universe is so deeply consistent? This uniform temperature is a profound clue, a cosmic fingerprint left over from the universe's fiery infancy. We call this the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. After the cosmos exploded into existence, it was a seething, opaque plasma of energy and particles. It took about 380,000 years for the universe to expand and cool enough for light to finally break free and travel across space. That first flash of light, stretched and diluted by 14 billion years of cosmic expansion, now reaches us as a faint microwave whisper. Satellites like the Planck Observatory have created exquisitely detailed maps of this ancient light. The picture they reveal is one of almost unbelievable smoothness. No matter which direction we point our telescopes, the temperature of this background radiation is 2.725 Kelvin, with variations so tiny they are only about 1 part in 100,000. Imagine a vast, perfectly calm ocean where the tallest wave is no bigger than a ripple on a swimming pool. That is the incredible uniformity of our infant universe. This sameness is not limited to temperature. The laws of physics themselves are universal. The force of gravity that holds you to the ground operates with the same exact strength in a galaxy 10 billion light-years away. Electromagnetism, the force behind light and chemistry, and the nuclear forces that power the stars are identical everywhere we look. The universe, it seems, plays by one single, unwavering set of rules. How could regions of space that have never been in contact, separated by distances so vast that light itself has not had time to travel between them, possibly agree on the thermostat? This is the core of the cosmic mystery. This staggering uniformity points toward a profound and powerful idea, a bedrock rule for the cosmos known as the Cosmological Principle. It declares that on the grandest scales, the universe is both homogeneous and isotropic. Homogeneous means the universe is the same everywhere, with matter and energy distributed evenly across the vastness of space. Isotropic means it looks the same in every direction you care to look. There is no special center and there are no preferred edges. We are not in a privileged location. The view from our galaxy is, in its essential character, the same as the view from any other galaxy anywhere. This principle is far more than a philosophical guess. It is a conclusion forced upon us by the evidence. When astronomers map the positions of millions of galaxies, they find them scattered in a vast cosmic web, a frothy structure of clusters and filaments. Yet, if you zoom out far enough, this intricate web averages out into a remarkably smooth and even distribution. The near-perfect uniformity of the cosmic microwave background radiation, that fossilized echo of the Big Bang, is the ultimate confirmation. It tells us this smoothness was baked into the universe from its very beginning. Embracing this idea was a monumental leap for science. For centuries, humanity naturally placed itself at the center of things, with the Earth and then our Sun as the focal points of creation. The cosmological principle shatters that comforting illusion. It tells us we live in a universe that is fundamentally democratic, where no place is any more special than another. This realization that we occupy a random, average corner of a uniform cosmos is the true starting point for modern cosmology. It frames the ultimate question. How did a universe born in a ferocious, chaotic fireball decide to play by the same rules everywhere, creating this stunningly level cosmic playing field? But if the universe is so uniform, why does it look so clumpy from our point of view? After all, the night sky is not a featureless soup. We see brilliant stars clustered into galaxies, galaxies gathered into sprawling clusters, and between them, immense dark voids of nearly empty space. This cosmic web is the very opposite of smooth, a tapestry of dense knots and vast, empty stretches. This apparent contradiction holds the key to understanding the true nature of the cosmological principle. The principle does not claim that your backyard is identical to the heart of a black hole. It reveals its truth only when we pull back, far back from the local details. The transition happens at a truly staggering scale, typically above 100 megaparsecs. A single megaparsec is itself an almost unimaginable distance, over 3 million light-years. So we are talking about viewing the universe in chunks larger than 100 million light-years across. At this monumental scale, the individual clumps and filaments of the cosmic web begin to blur and average out. The towering galaxy clusters and the cavernous voids, so dramatic up close, start to resemble the gentle hills and valleys of a vast, level plain. Think of it like looking at a beach from just a few inches away. You see every distinct grain of sand, every sharp shell fragment, every pebble. The landscape seems wildly irregular and complex, but if you stand up and view the entire shoreline from a distance, that intricate detail merges into a single, smooth, golden band. The universe operates on a similar principle. Our local neighborhood, our galaxy and its nearby companions, is just one grain of sand on an unimaginably vast cosmic beach. When our telescopes map the universe on these grand scales, the lumpiness vanishes. The distribution of matter and energy becomes profoundly even, a homogeneous sea. This is the powerful dual reality of our cosmos. It is both intricately structured and profoundly uniform, a testament to the forces that shaped it from a state of perfect smoothness into the complex web we call home. This deep and fundamental uniformity leads us directly to one of cosmology's greatest puzzles. We call it the horizon problem, and it challenges our most basic understanding of cause and effect. To grasp the problem, we must first understand the concept of a cosmic horizon. Since the Big Bang, the universe has been expanding for a finite amount of time, about 13.8 billion years. Because nothing can travel faster than light, there is a limit to how far any influence, any signal, any whisper of heat could have possibly traveled in all that time. This defines our observable universe, a sphere centered on us, bounded by a horizon beyond which we cannot see and with which we could never have interacted. Now take that concept and apply it to the early universe. Look at the cosmic microwave background, that baby picture of the cosmos. The light from one side of this background has traveled for 13.8 billion years to reach us. The light from the exact opposite side of the sky has also traveled for 13.8 billion years to reach us, but here is the stunning part. Those 2 points on opposite sides of the sky have never been in contact with each other. In the entire history of the universe, there has not been enough time for light or any form of information to have traveled from one to the other. They are, and always have been, completely causally disconnected. They have never exchanged a single photon, never shared a single bit of heat, never communicated in any way. And yet, their temperatures are identical to an astonishing precision of 1 part in 100,000. How is this possible? How could 2 separate ovens, placed back to back with an impenetrable wall between them, somehow end up set to the exact same temperature without ever talking to each other? This is the paradox. The universe appears to have coordinated a perfect, uniform temperature across regions that, according to the standard Big Bang model, should have had no way to even know the other existed. It is as if you walked into a vast library and found that every single book written by authors who lived in complete isolation on different continents told the exact same story, word for word. The only logical conclusion is that they must have all copied from a common source. For our universe, this points to a dramatic and transformative chapter in its very first moments. a period that forced the entire cosmos into a state of perfect, synchronized agreement. The only way to solve this paradox of disconnected twins is to realize they were not always strangers. They were once intimate neighbors living in the same tiny room. This is the breathtaking idea of cosmic inflation, a theory that rewrites the very first chapter of our universe's story. In its conventional telling, the Big Bang begins with a hot, dense state and then expands at a stately, measured pace. But inflation proposes something far more dramatic. In the first sliver of a second after existence began, a period so brief it is almost meaningless to our human sense of time, the universe underwent a growth spurt of unimaginable ferocity. Space itself did not just expand, it exploded outward at a rate that defies all intuition. During this inflationary epoch, the universe did not merely double in size. It doubled and then doubled again and again in a relentless exponential cascade. The total expansion factor was staggering, at least 10 to the power of 26. To put that number into perspective, imagine a single atom, a proton smaller than anyone can truly picture. Now, imagine inflating that single proton until it is larger than our entire observable universe, a sphere billions of light years across. That is the scale of the transformation we are talking about. Before this hyper-expansion began, there was a tiny, subatomic patch of the nascent cosmos. Crucially, this microscopic region was small enough for light to cross it in an instant. Every part of it was in constant, intimate contact with every other part. Heat could flow freely, and forces could interact, allowing this entire seed to settle into a state of perfect thermal equilibrium. It reached a uniform temperature, just as a cup of coffee left to sit will eventually become the same warmth throughout. Then inflation struck. This period of unimaginably rapid expansion did not create new matter or energy from nothing. Instead, it took that tiny, smooth, and thermally balanced patch of spacetime and stretched it to a size so colossal that it encompasses everything we can see today and far, far beyond. The entire observable universe, with all its hundreds of billions of galaxies, was once crammed into a region smaller than a single proton. This single, elegant idea solves the horizon problem completely. Why does the cosmic background radiation have the same temperature on opposite sides of the sky? Because those 2 points, now separated by tens of billions of light years, were once right next to each other in that primordial, ultra-dense seed. They were in perfect thermal contact before inflation blew them apart. They had all the time in the world to agree on the thermostat, back when their world was impossibly small. Inflation takes the library of identical books and reveals their true history. They are not the work of isolated authors who somehow wrote the same story. They are all copies of a single, original manuscript, a master text that was then photocopied and distributed on a cosmic scale, with each copy becoming a vast region of space. This violent, transformative stretching did more than just solve the smoothness problem, however. It also planted the seeds for everything to come. That primordial seed, born from the quantum foam, was not perfectly serene. Before inflation began, the universe at its smallest scales was a turbulent sea of potential, a chaotic froth where energy densities fluctuated wildly from one point to the next. It was a landscape of unimaginable chaos, with sharp peaks of intense energy and deep valleys of relative calm, all popping in and out of existence on timescales too brief to comprehend. This was the universe's raw, untamed potential. Then, in an instant, the inflationary mechanism was triggered. Think of it as the universe taking a single, deep, unifying breath before its great expansion. What happened next was not like blowing up a balloon slowly with a pump. It was more like a cosmic explosion of space itself. The fabric of the cosmos expanded at an exponential rate, so ferociously that it stretched every irregularity, every wrinkle, and every quantum jitter to proportions so vast they became cosmically insignificant. Imagine a crumpled piece of paper full of sharp, chaotic creases. Now imagine stretching that paper until it is the size of a continent. From your new, grand perspective, every tiny fold and wrinkle has been flattened into near-perfect smoothness. The paper is not perfectly flat, of course, but its largest scale features are now profoundly even. This is precisely what inflation did to our universe. It took those wild quantum fluctuations and stretched them so dramatically that they were ironed out across the observable cosmos. The result was the remarkably flat and uniform expanse we detect in the cosmic microwave background. The entire observable universe became that single, smooth piece of paper with only the faintest of imprints left behind. This process did not just smooth the temperature, it solved the geometry of the cosmos as well. The violent stretching forced the universe toward what we call flatness, a specific and stable geometric state where parallel lines remain parallel and the fabric of space-time is not intrinsically curved. This is why the horizon problem vanishes. Those 2 points on opposite sides of the sky, which could never have communicated under the old rules, were intimate neighbors in that pre-inflationary seed. They were close enough to share energy and reach a uniform temperature before the great stretching pulled them apart to become the horizons of our world. Inflation gave the entire cosmos a shared childhood, a common origin point from which everything we see could emerge perfectly synchronized. Yet this great smoothing did not leave the cosmos featureless. Inflation performed a kind of cosmic magic, taking the tiniest possible irregularities and magnifying them into the blueprint for all of creation. That primordial patch, for all its apparent smoothness, was not perfectly uniform. At the quantum level, it was a seething, bubbling foam. Empty space itself was not truly empty, but a stage for constant, fleeting fluctuations. Pairs of particles and their antiparticles would wink into existence for an unimaginably brief moment, borrowing energy from the vacuum before annihilating and returning it. This chaotic dance created minute ripples in the very fabric of spacetime itself. These were quantum fluctuations, random hills and valleys in the density of energy, so small they are almost beyond description. Then inflation struck. As space expanded at a fantastic rate, it did not simply erase these tiny wrinkles. Instead, it stretched them, locking them in and magnifying them from the quantum realm to the cosmic scale. A microscopic variation in density smaller than a single atom was suddenly inflated to a size spanning thousands of light years. These amplified ripples became the gravitational seeds for all future structure. Think of a perfectly smooth, calm lake on a windless day. The surface is like glass, but just beneath, the water is always moving, vibrating with a faint, microscopic shimmer. Now imagine if you could suddenly freeze the entire lake solid in an instant. That faint shimmer, that subtle vibration, would be captured and preserved as a permanent, frozen texture across the entire surface of the ice. Inflation did exactly that to the early universe. It took the faint quantum shimmer of space-time and froze it into the very large-scale structure of the cosmos. These minute differences in density were crucial. In regions where the energy was ever so slightly denser, gravity had a tiny bit more to work with. Over billions of years, that slight gravitational advantage would pull in more and more matter from the surrounding space. The slightly denser patches grew into vast clouds of gas, which collapsed to form the first stars, which gathered into galaxies, and those galaxies clustered into the great cosmic web we see today. The slightly less dense regions, by contrast, evolved into the vast, empty voids that separate these structures. This direct link between the quantum and the cosmic is written in the sky. The tiny temperature variations we see in the cosmic microwave background, those 1 part in 100,000 differences, are not mere static. They are the fossilized imprint of those original quantum fluctuations. Each slightly warmer spot on the map corresponds to a region that was marginally denser in the early universe, a future seed for a galaxy cluster. each slightly cooler spot marks a region that was destined to become one of the great cosmic voids. The entire intricate architecture of our universe, from the grandest galaxy superclusters to the planet you stand on, owes its ultimate origin to these random subatomic tremors stretched across the cosmos in its first fleeting moment. We are the children of quantum noise magnified to a cosmic symphony. So if inflation truly happened, it should have left behind unmistakable fingerprints. The theory makes several bold, testable predictions, and over the past few decades, our telescopes have gone hunting for them. The first major prediction concerns the shape of the cosmos. Inflation's violent stretching should have forced the universe into a state of geometric flatness. Think of the surface of a perfectly flat sheet of paper, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. If the universe were curved like a sphere or a saddle, those rules would break down. When astronomers meticulously measured the universe's large-scale geometry, they found exactly what inflation foretold. The cosmos is flat to an astonishing precision, a finding that fits the inflationary model perfectly. The second prediction lies in the specific character of the cosmic background radiation. Inflation did not just make the universe smooth, it also imprinted a particular pattern of fluctuations onto it. The theory predicted that these primordial ripples should follow a nearly scale invariant pattern. This means that the tiny variations in density, the seeds for all future galaxies, should have been imprinted with roughly the same strength, regardless of the size of the patch of sky you examine. This is a very specific signature. When satellites like WMAP and Planck mapped the cosmic microwave background in exquisite detail, the data revealed a pattern of hot and cold spots that matched the inflationary prediction with stunning accuracy. The blueprint for the entire cosmic web was drawn in that first explosive moment, and we can still read its code in the ancient light from the dawn of time. Perhaps the most dramatic prediction, however, is the existence of primordial gravitational waves. Inflation proposes that the universe underwent a period of incredibly rapid expansion, a process so violent that it would have sent powerful ripples through the very fabric of spacetime itself. These are not waves of light or sound, but waves in the geometry of the cosmos, stretching and compressing space as they travel. Finding these waves would be the ultimate smoking gun for inflation, a direct echo of the universe's explosive birth. Experiments are actively hunting for their faint signature, often by looking for a distinctive swirling pattern they would have imprinted on the polarization of the cosmic microwave background. The success of its first two predictions has made cosmic inflation the leading framework for understanding our universe's origin. It explains the flatness, the smoothness, and the specific pattern of seeds for galaxies in one elegant, powerful package. Yet the hunt for that final, conclusive piece of evidence continues. The detection of primordial gravitational waves would not just confirm inflation, it would open a window directly into the universe's very first moment, a time before which our current physics breaks down completely. Until then, we are left with a theory that explains so much of what we see, a story written in the geometry of space and the faint afterglow of creation. Despite its elegant success, cosmic inflation is not the only idea on the table. The quest to explain our uniform cosmos has spawned other compelling, if more speculative, theories. One of the most dramatic is the ekpyrotic universe model. This concept envisions our universe existing on a three-dimensional membrane or brain, floating within a higher dimensional reality. In this scenario, the Big Bang was not a singular point of creation, but the aftermath of a cataclysmic collision between our brain and a neighboring one. Picture the entire cosmos as a vast, silent sheet of paper. Another sheet, a parallel universe, drifts slowly toward it in the hidden dimensions. When they meet, the impact is not destructive but creative. The colossal transfer of energy from the collision reheats our brain, effectively resetting it into the hot, dense state we recognize as the beginning of our cosmic cycle. This violent encounter naturally smooths out the universe, just as two panes of glass pressed together force out any air bubbles between them. The collision of these branes would have ironed out any prior wrinkles, leaving behind the remarkably uniform cosmos we observe. It is a cyclical vision of the universe with no true beginning or end, only endless cycles of collision, expansion, and cooling. While it elegantly accounts for the smoothness and flatness, the ekpyrotic model also makes predictions, particularly about the pattern of gravitational waves that differ from standard inflation, offering a potential way to test this breathtaking idea. Another radical proposal challenges one of physics' most sacred tenets. The variable speed of light hypothesis dares to ask, what if the speed of light was not always constant? In its earliest moments, if light traveled at a vastly faster rate, the horizon problem simply vanishes. Distant regions of the nascent universe, which were out of communication range under the standard speed limit, could have easily exchanged energy and information when light was unshackled. It is as if two towns, previously separated by an impassable mountain range, were suddenly connected by a futuristic hyperloop. They could instantly share resources and agree on a common temperature before the rules of the road changed and the connection was severed. This idea directly solves the causality issue, but it comes at a profound cost. The constancy of the speed of light is the cornerstone of Einstein's theory of relativity, a principle woven into the very fabric of modern physics. Modifying it requires a fundamental rewrite of our most successful theories of how the universe operates, a step many physicists are reluctant to take without overwhelming evidence. So where does this leave us? Inflation remains the dominant framework because it is a powerful, self-contained narrative that explains a wide range of observations, from the flat geometry to the specific pattern of cosmic seeds. Its competitors, while brilliant in their own right, often solve one problem while creating others or lack the same breadth of predictive power, yet their existence is vital. They are the necessary challengers, the alternative hypotheses that keep cosmology honest and push our understanding toward its limits. The true nature of the universe's first moment remains an open question, a mystery written in the sky, waiting for a definitive signal to tip the scales. This incredible fine-tuning is known as the flatness problem, and it is every bit as puzzling as the horizon mystery. The universe's geometry is not a matter of simple preference. It is dictated by the total density of all the matter and energy contained within the cosmos. There is a specific, critical density required for the universe to be perfectly flat, a delicate balance between the outward push of expansion and the inward pull of gravity. If the actual density were even slightly above this critical value, the universe would be closed, curving back on itself like the surface of a sphere. If it were even slightly below, it would be open, curving outward like a saddle. For billions of years, astronomers tried to measure this cosmic curvature to see which shape our universe had taken. The answer, when it finally came, was a profound surprise. Our universe is flat. Not just approximately flat, but astonishingly, exquisitely flat. The observed density is pinned to that critical value with a precision that is almost impossible to comprehend. This presents a monumental puzzle when we rewind the cosmic film. The force of gravity works relentlessly over time, pulling the universe away from this delicate balance. If the universe is this perfectly flat today, then in its first moments, its density must have been tuned to an almost impossible degree. How precise are we talking about? At just 1 second after the Big Bang, the universe's density had to be fine-tuned to within 1 part in 10 to the power of 60. That number is so large it defies all everyday analogy. It is a 1 followed by 60 zeros. Imagine you needed to balance a cosmic pencil on its tip, not for a second, but for 14 billion years. To achieve that, the sharpened point would have to be so perfectly aligned at the start that its angle was correct to a margin of error smaller than the size of a single atom compared to the entire observable universe. Without some powerful mechanism to force it into that state, such a perfect initial condition seems like the most unbelievable of cosmic coincidences. Why would the universe be born with its density dial set to such an impossibly specific value? The flatness problem suggests that this was not a lucky accident, but the direct result of a physical process that actively drove the universe toward this geometric perfection. This astonishing flatness was not a lucky starting point, but the inevitable outcome of that violent, exponential stretching. Inflation acted as a cosmic iron, relentlessly smoothing out the geometry of the universe. To see how this works, picture a balloon before you blow it up. Its surface is small, wrinkled, and full of sharp, pronounced curves. If you were a tiny ant living on that uninflated surface, you would have no doubt that your world was highly curved. Every direction you looked, the ground would bend away from you dramatically. Now, begin to inflate the balloon. As it expands, the rubber stretches taut. The tiny patch of surface you are standing on grows and grows. Those sharp wrinkles are pulled smooth, and the intense local curvature stretches out into a gentle, vast expanse. From your new, local perspective, the ground beneath your feet now appears almost perfectly flat. The curvature is still there, of course, but it has been diluted over such a large area that it is virtually undetectable to you. This is precisely what cosmic inflation did to our universe. Before inflation, the cosmos could have been born with any arbitrary shape, wildly curved like a saddle or tightly closed like a sphere. It was a tiny, crumpled, subatomic thing. Then, in that fraction of a second, inflation blew it up. The observable universe expanded by a factor of at least 10 to the 26, transforming from a speck to a volume encompassing everything we can see. This phenomenal stretching forced any initial curvature to be spread so thin, across such an immense volume, that the resulting geometry within our observable horizon became indistinguishable from perfect flatness. The universe was driven inexorably toward that critical density, not by chance, but by the sheer mechanics of hyper-fast expansion. The pencil did not need to be balanced on its tip with impossible precision from the start. Instead, inflation grabbed the pencil and stretched the entire floor beneath it until the surface was so vast and level that the pencil could not help but stand perfectly upright. This elegant resolution removes the need for that unimaginable 1 in 10 to the 60 fine-tuning. The flatness of our universe is no longer a mysterious, finely tuned initial condition. It is a natural prediction, a direct consequence of the universe undergoing a period of breathtaking growth, ironing out its wrinkles and leaving behind the level cosmic plane we measure today. This relentless expansion of inflation leads us to a staggering possibility, one that redefines our place in reality. The mechanism that smoothed our universe might never have truly turned off. In the framework known as eternal inflation, the exponential stretching of spacetime is not a single, finished event. Instead, it is a runaway process that, once started, is almost impossible to stop completely. Think of it like a pot of water coming to a boil. Bubbles of steam form at the bottom and rise to the surface. In eternal inflation, the background, the seething quantum foam, is the boiling water, continuously undergoing hyper-fast expansion. But within this frenzied medium, pockets of stability can form. These are the bubbles of steam. In each of these regions, the inflationary process ends locally, allowing a calm, orderly universe like our own to nucleate and form within the greater, ever-inflating background. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one such bubble in an infinite, frothing sea. This is the multiverse. It is not a separate place you could travel to, but a vast meta-reality where countless pocket universes are constantly being born, each with its own unique properties. The physical constants we take for granted, the strength of gravity, the mass of an electron, the very number of dimensions of space, might not be fundamental laws written in stone. They could be local by laws, effective only within our particular bubble. In another universe, the force of gravity might be too weak to form stars. In another, electromagnetism might be so strong that atoms could never stabilize. The cosmic lottery has produced a near-infinite array of possible worlds, most of them barren and lifeless, with physical laws that could not support any complex structure, let alone life. This radical idea offers a potential explanation for one of the deepest mysteries: why our universe seems so finely tuned for our existence. If the fundamental constants were even slightly different, carbon-based life would be impossible. Stars would not burn, chemistry would not function. In a single, lonely universe, this perfect balance seems like an unbelievable coincidence, a miracle. But within the context of the multiverse, the mystery begins to fade. With an infinite number of trials, with every possible combination of physical constants being realized somewhere, it is no longer surprising that we find ourselves in one of the rare, hospitable bubbles where the conditions for life accidentally came together. We are not the purpose of the cosmos, but simply the lucky inhabitants of a universe that works. While this remains a highly speculative and controversial idea, it shows how the quest to understand our universe's profound uniformity has led us to the very edge of scientific imagination, forcing us to contemplate a reality far grander and more strange than we ever dreamed. But what is this cosmic scaffolding made of? The answer lies in a substance so elusive it has never been directly seen, yet its gravitational signature is written across the sky. Dark matter makes up roughly 27% of the entire mass-energy content of the cosmos, a dominant but invisible player in the story of structure. Think of the universe as a vast construction site. Ordinary matter, the stuff of stars, planets, and our own bodies, is like the lumber, bricks, and glass. But dark matter is the steel framework, the unseen skeleton that holds everything together. Without its immense gravitational pull, the universe would look nothing like it does today. In the early cosmos, after inflation had stretched and smoothed the quantum seeds, dark matter was the first to respond. Because it does not interact with light or other electromagnetic forces, it was free to begin clumping under gravity long before normal matter could. While the primordial plasma of protons and electrons was still a searing, opaque fog, buffeted by the pressure of light, dark matter could quietly settle into a vast, invisible web of gravitational wells. This web became the template for all future construction. When the universe finally cooled enough for atoms to form and light to travel freely, ordinary matter fell into the deep gravitational pits carved out by the dark matter. Gas streamed along these invisible filaments, pooling at the dense intersections and igniting into the first stars and galaxies. Every majestic spiral galaxy and every colossal cluster we see is therefore embedded within a much larger, massive halo of this mysterious substance. The reason the universe appears so uniform on the largest scales is because this dark matter scaffold is itself distributed with remarkable smoothness. Its gravitational influence averages out across hundreds of millions of light years, enforcing the homogeneous cosmos demanded by the cosmological principle. We are left with a profound realization. The beautiful, structured universe we observe, with its glittering islands of light, is merely the visible decoration on an immense, hidden architecture of dark matter. This invisible cosmic scaffold, however, is not the only force shaping our universe's destiny. A far more dominant and mysterious power is at work, one that governs the expansion of space itself. We call it dark energy. This enigmatic component makes up about 68% of everything in the cosmos, and its sole effect appears to be a relentless push, accelerating the expansion of the universe. Think of gravity as the great cosmic architect tirelessly working to pull matter together into structures. Dark energy, in contrast, acts as the cosmic landscaper on a grand scale, stretching the very fabric of space-time and smoothing everything out. As galaxies rush away from each other at ever-increasing speeds, the vast distances between them grow at an accelerating rate. This relentless expansion does not create new matter, it simply dilutes what is already there. The great clusters and superclusters, the very filaments of the cosmic web, are being stretched thin across the growing void. Over immense spans of time, this process drives the universe toward an even greater state of homogeneity. The clumpy, intricate structure we see today will, in the far future, become increasingly washed out and dispersed. Imagine a drop of ink in a glass of water. At first, it forms a dark, concentrated cloud, but if you slowly add more and more water, constantly stirring, the ink eventually disperses until the entire glass is a uniform, faint shade. Dark energy is that constant stirring of the cosmic glass, ensuring that the structures we find so familiar will one day fade into a far more even and lonely cosmos. This accelerated expansion guarantees that the universe's large-scale uniformity is not just a relic of the past, but the inevitable direction of its future. The great cosmic voids will win in the end, growing ever larger as the islands of light we call galaxies are pushed apart into isolated darkness. These frozen sound waves offer us a standard ruler etched into the cosmos. In the primordial plasma of the early universe, before atoms could even form, matter and light were locked in a ferocious tug of war. Gravity would try to pull a clump of protons and electrons together, but the intense pressure from the trapped radiation would violently push it all apart. This created a series of pressure waves, much like sound waves rippling through air, that propagated outward from every slight over density. For hundreds of thousands of years, these spherical sound waves expanded through the searing hot soup of the infant cosmos. Then, in a single, transformative moment, the universe cooled enough for atoms to form. The radiation which had been trapped suddenly broke free and streamed across space, becoming the cosmic microwave background we see today. With the radiation gone, the pressure that had been driving the waves vanished instantly. The waves froze in place, leaving behind a distinct spherical shell of matter around each of those original seeds. This fossilized imprint is a Barrian acoustic oscillation. The key is that all these waves traveled at the same known speed, the speed of sound in that primordial plasma, for the exact same amount of time before the universe became transparent. This means they all reached the same maximum size before freezing. That specific distance, about 500 million light-years across, became a standard ruler stamped onto the fabric of the universe. Today, we can still see its echo. When astronomers map the positions of millions of galaxies, they find a subtle but undeniable preference for pairs of galaxies to be separated by this exact scale. It is as if the cosmos is dotted with countless invisible spheres, all with the same radius, with galaxies tending to cluster on their surfaces. By measuring this preferred separation in the sky, astronomers can do something extraordinary. They can measure how the geometry of the universe has stretched over billions of years. If the universe were curved, these standard rulers would appear distorted at different distances. If the universe is flat, as inflation predicts, then the rulers will maintain their expected size. The data is unequivocal. Across vast cosmic distances, these frozen sound waves confirm the universe's large-scale flatness and its remarkable uniformity, providing one of the strongest modern tests of the cosmological principle. We are literally measuring the expansion history of everything using the ghost of a sound from the universe's first cry. This grand cosmic consensus, however, is now facing a serious challenge. A single, stubborn number is creating a rift in our understanding of the universe's expansion. We call this the Hubble Tension. At its heart is the Hubble constant, a value that measures how fast the cosmos is expanding today. For decades, cosmologists have pursued this number with two powerful, independent methods. The first method looks back to the dawn of time, using the cosmic microwave background as a pristine starting point. By analyzing the subtle patterns in that ancient light, we can run the cosmic film forward, calculating precisely what the expansion rate should be today, based on our well-tested model of the universe. The second method measures the universe as it is now, observing the apparent brightness and recession speeds of nearby supernova and other stellar markers to get a direct local reading of the expansion rate. These are not just two different techniques, they are two different eras of cosmic history speaking to us, and they are telling us two different stories. The early universe method gives one value for the Hubble constant. The late universe method gives a value that is consistently, significantly faster. The discrepancy is not large, only about 10%, but it is far greater than the estimated margins of error for either measurement. It is a persistent, glaring inconsistency that has withstood years of re-examination and improved data. Imagine two of the world's most precise clocks, both built by master craftsmen, one set at the beginning of time and one set today. You expect them to tick in perfect sync, but they are steadily drifting apart. This is the essence of the Hubble tension. So what could be causing this crack in our cosmic model? One possibility is the existence of unknown physics. Perhaps there is a new, exotic form of energy or a previously unknown type of neutrino that briefly influenced the expansion rate in the universe's adolescent years, throwing off the connection between the ancient past and the present day. Another, more unsettling idea is that this tension points to a flaw in our fundamental assumption of a perfectly homogeneous universe. What if, on the very largest scales, the cosmos is not quite as uniform as we thought? What if our local region of space is part of a vast cosmic void, an underdense bubble that is expanding just a little bit faster than the universal average? From our perspective inside this bubble, the expansion would appear accelerated, creating the exact kind of discrepancy we observe. This would mean we are not in a truly average place after all, subtly challenging the cosmological principle itself. Of course, there is always the chance of a hidden systematic error, a subtle miscalibration in our measurements that has eluded the world's best scientists. Yet as the data grows more precise and the tension remains, the simpler explanations are fading. This is not a sign that science is broken, but that it is working exactly as it should. The Hubble tension is a beacon guiding us toward the next revolution in cosmology. It reminds us that our map of reality is still being drawn and that the universe always has one more secret to share. This specific cosmic recipe has a name, the Lambda CDM model, and it represents our most complete understanding of the universe's ingredients. The entire cosmos, everything that is and ever was, can be broken down into three simple but profound components. A mere 5% is the ordinary matter that makes up every star, every planet, and every one of us. Roughly 27% is dark matter, the invisible gravitational glue that holds galaxies together. And a dominant 68% is dark energy, the mysterious force accelerating the expansion of space itself. This is not a random assortment. This precise mix is the direct result of the initial conditions forged during inflation, and it is the ultimate reason our universe appears so flat, so uniform, and is expanding at an ever-increasing rate. Imagine baking a cosmic cake. Inflation provided the initial, perfectly smooth batter. Dark matter acts as the structural flour, giving the cake its shape and form, creating the gravitational wells where galaxies can rise. Ordinary matter is the sugar and flavor, the visible, complex structures we actually see. And dark energy is like a relentless leavening agent, constantly causing the entire cake to expand, ensuring it rises evenly and never collapses back in on itself. This specific combination of ingredients is what produces the universe we measure. The initial smoothness from inflation was preserved and enhanced by dark matter's gravitational pull, which organized structure without creating wild irregularities on the largest scales. Meanwhile, the overwhelming presence of dark energy guarantees that the grand cosmic tapestry is being stretched toward an even greater state of homogeneity over time. The Lambda CDM model is more than just a list of parts, it is a story of balance. It explains how a universe can be both richly structured and profoundly uniform, how it can be filled with brilliant islands of light while still obeying the cosmological principle on the grandest of stages. This is our standard model of cosmology, a testament to how far we have come in deciphering the universe's deepest secrets from a few fundamental clues. But this cosmic democracy faces a potential rebellion. The universe might not be perfectly isotropic after all. Astronomers have stumbled upon a strange and unsettling feature in the cosmic microwave background, one they have dramatically nicknamed the axis of evil. This is not a malevolent force, but a claimed alignment of certain large-scale features in the ancient light that seems to define a preferred direction in space. Imagine spinning a globe and finding that all the world's major mountain ranges are mysteriously aligned along a single line running from the north to the South Pole. This is the kind of unexpected order that the axis of evil appears to represent in the cosmos. The hot and cold spots in the microwave background, the very seeds of galaxies, show a curious correlation across billions of light years, suggesting the universe might have a subtle equator and poles. If this alignment is real and not a statistical fluke, it would be a direct challenge to the cosmological principle. It would mean that on the largest scales, the universe has a preferred axis, a fundamental lopsidedness that would force us to rewrite our textbooks. The evidence, however, is hotly debated. The signal is faint, buried at the very limits of what our satellites can detect, and many scientists argue it is simply a trick of the data, a cosmic mirage created by the way we process the map or by foreground interference from our own Milky Way galaxy. Yet it refuses to go away entirely. If the axis of evil is confirmed, the implications are profound. It could point to a pre-inflationary universe with a residual structure that never got completely erased, or to exotic physics that imprinted a direction onto spacetime itself. It serves as a crucial reminder that our grandest models are provisional, always subject to the next unexpected discovery written in the stars. To grasp this profound uniformity, we must journey back to the very first moments of everything. Rewind the cosmic clock to a time before the first star ignited, before the first atom formed, to a state of almost unimaginable ferocity. The universe was not filled with galaxies or empty space, but was a searingly hot, dense plasma, a primordial soup of fundamental particles. In this cauldron of creation, temperatures were so high that the building blocks of matter as we know them could not even exist. Protons and neutrons had not yet formed from their constituent quarks. Electrons, positrons, and photons were all trapped in a frenzied, relentless dance. This was a world of pure energy and constant, violent interaction. A photon of light could not travel a microscopic distance without slamming into a free electron, being scattered and absorbed in a chaotic blur. This constant, intimate contact was the key to its remarkable smoothness. With particles colliding trillions upon trillions of times every second, any local hotspot would be instantly dissolved, its energy rapidly shared with its cooler surroundings. The entire cosmos was in a state of perfect thermal equilibrium, a single, unified entity with a uniform temperature and density throughout its entire, albeit tiny, volume. This was not a calm, simmering pot, but a raging, boiling maelstrom where equilibrium was maintained by sheer, brutal force. It is from this state of inherent, forced smoothness that our entire observable universe would eventually emerge. The great inflationary expansion did not create this uniformity from chaos. It simply took this already smooth, hot soup and stretched it. It preserved that perfect thermal equilibrium and magnified it from a subatomic speck to a cosmic canvas billions of light years across. The initial conditions for a uniform cosmos were not a lucky accident. They were the only possible outcome of a universe that was once small enough, hot enough, and dense enough for every single part of it to be in constant, blistering conversation with every other part. This primordial soup held the entire future of chemistry in its grasp. For the first 3 minutes of cosmic history, the universe was still a blistering nuclear furnace, hot and dense enough to forge the very first atomic nuclei in a process we call Big Bang nucleosynthesis. As the cosmos expanded and cooled from its initial inferno, it crossed a critical threshold. Protons and neutrons, newly formed from the quark-gluon plasma, could finally begin to stick together. What followed was a frantic 3-minute sprint to build the lightest elements. Protons, which are single hydrogen nuclei, were the most abundant building blocks. They began to collide, fusing with neutrons to form deuterium, a heavy isotope of hydrogen. This was the crucial first step. Once deuterium nuclei formed, they could rapidly fuse further, capturing more protons and neutrons to create helium. The entire universe acted as a single, unimaginably vast particle accelerator, with nuclear reactions occurring everywhere at once. But this window of opportunity was incredibly brief. As the universe continued to expand, its density and temperature plummeted. After just a few hundred seconds, the cosmos had cooled and thinned so much that the energy of colliding particles was no longer sufficient to overcome the electrical repulsion between their positive charges. Nuclear fusion slammed to a halt. The cosmic forge had shut down, leaving behind a specific, frozen mix of primordial elements. The universe was left with a sea of hydrogen nuclei, about 75% by mass. Nearly 25% was helium-4, the most stable light nucleus, and there were only trace amounts of deuterium, helium-3, and a tiny sprinkling of lithium-7, the next element in the chain. The entire periodic table beyond this simple beginning would have to wait billions of years for the hearts of stars to form. The true power of this story lies in its predictive precision. The theory of Big Bang nucleosynthesis makes a very specific forecast. Given the known laws of nuclear physics and the conditions of the early universe, it calculates the exact percentages of these light elements that should have been cooked in that first 3-minute burst. Astronomers can then test this prediction by looking at the most ancient, pristine objects we can find, like certain old stars and distant clouds of gas that have not been contaminated by later generations of star formation. The agreement is nothing short of spectacular. Everywhere we look, in every corner of the cosmos, the oldest material shows the same ratio of hydrogen to helium, the same tiny fraction of deuterium, and the same minuscule amount of lithium that the theory demands. This universal recipe is a powerful echo of that initial, uniform state. The process only works if the entire cosmos was once a single, well-mixed cauldron with the same temperature and density everywhere. If the early universe had been lumpy, with some regions much hotter or denser than others, the nuclear reactions would have proceeded at different rates. Some patches would have burned all their hydrogen into helium, while others would have left behind only pure hydrogen. The final average we observe today would be a messy, inconsistent blend, not the clean, precise pattern we see etched across the sky. The fact that we can measure the deuterium in a distant quasar's light and find it perfectly matches the abundance in a primordial gas cloud in our own galactic backyard is a testament to that profound initial smoothness. Big Bang nucleosynthesis is more than just the origin of the first elements. It is a frozen moment in time, a cosmic fingerprint that confirms our universe was born from a hot, dense, and deeply uniform beginning. The Sloan Digital Sky Survey has painted a monumental portrait of our cosmic neighborhood, charting the positions of millions of galaxies. What emerges is not a random scattering of lights, but an intricate architecture of breathtaking scale and beauty. This is the cosmic web, a vast, interconnected network where galaxies congregate in massive clusters, thread along delicate filaments that stretch for hundreds of millions of light years and are separated by immense, cavernous voids of near emptiness. It is a universe of stunning complexity, a tapestry woven from light and shadow. Yet, within this apparent chaos lies a profound order. When cosmologists apply powerful statistical tools to these maps, they make a remarkable discovery. If you analyze the universe in chunks smaller than about 300 million light-years, it looks wildly lumpy, dominated by these clusters and voids. But the moment you zoom out to larger scales, that intricate detail begins to average away. The sharp peaks of the clusters and the deep troughs of the voids start to cancel each other out. What remains is a sea of remarkable uniformity. The distribution of matter, when viewed on these grandest of stages, becomes profoundly even. This is not a theoretical guess, it is a direct observational fact measured from the light of countless galaxies. The sprawling cosmic web, for all its intricate majesty, is merely a pattern of gentle ripples on the surface of a deep, homogeneous ocean. This statistical smoothness is one of the strongest validations of the cosmological principle we have. It confirms that we do not live in a special or unique place, but in a universe that plays by the same rules and exhibits the same large-scale structure no matter where you are. This relentless expansion points toward a future of profound isolation. The cosmic acceleration driven by dark energy is not a temporary phase. It is a fundamental feature of our universe that will only intensify with time. The galaxies we see today, scattered like distant ships on a dark ocean, are already drifting away from us, but in the far future, this drift will become a final, irreversible flight. Every galaxy not gravitationally bound to our own local group will eventually be pushed beyond our cosmic horizon. Their light, no matter how powerful our telescopes become, will simply be unable to reach us as the space between us expands faster than the light can travel across it. One by one, those extragalactic stars will wink out of the sky, not from dying, but from being swept beyond the edge of forever. The universe will not end with a cataclysm, but with a quiet fading. Our descendants, if any remain in that unimaginably distant era, will gaze up at a night sky that is almost perfectly black. The magnificent cosmic web, with its brilliant clusters and filaments, will have vanished from view. All that will remain visible are the aging stars of our own merged galaxy, a single, lonely island in an ocean of expanding nothingness. This is the ultimate expression of the cosmological principle, a universe so vast and empty that from any one point it appears utterly homogeneous and dark. The great drive toward sameness, begun in the first inflationary moment, will reach its logical and silent conclusion, leaving behind a cosmos where the very concept of a varied universe is a forgotten memory. That grand cosmic consensus now rests on the shoulders of a ghost. The inflattened field, the hypothetical engine of inflation, remains one of the greatest unsolved puzzles. We know what it must have done, stretching the universe from a quantum speck to a cosmic expanse, but we have no idea what it actually was. Was it a single, fundamental force or a confluence of many? Its nature is completely unknown, a phantom driver that vanished after its brief, universe-altering task was complete. The hunt for its signature has therefore turned to the most subtle of echoes, primordial gravitational waves. These ripples in space-time are the direct prediction of inflation's violent expansion, a cosmic tremor that should still be resonating through the universe today. Detecting them would be like finding the fossilized footprints of the inflattened field itself, confirming its reality and potentially revealing its properties. Enormous efforts are underway with next-generation observatories like LISA, a space-based gravitational wave detector being designed to listen for this faint whisper from the dawn of time. Meanwhile, back on Earth, projects like the CMB S4 are building incredibly sensitive telescopes to scan the cosmic microwave background for the specific swirling pattern, known as B-mode polarization, that these primordial waves would have imprinted on the ancient light. Finding that pattern would be the ultimate smoking gun, and then there is the persistent headache of the Hubble tension. This discrepancy in the universe's expansion rate is more than a minor statistical fluke. It is a beacon pointing toward potential new physics. Could it be evidence of dark energy evolving over time, or perhaps an unknown particle that briefly altered the cosmic expansion? To investigate, astronomers are turning to vast new sky surveys. The Legacy Survey of Space and Time, or LSST, at the Vera C. Rubin Observatory will map billions of galaxies in unprecedented detail, providing a colossal new dataset to measure cosmic distances and refine our understanding of the universe's expansion history. This is not the end of a story, but a thrilling new chapter. Each of these experiments is a voyage into the unknown, a direct test of our most fundamental ideas about cosmic origins. The answers they find may not just confirm our theories, but could completely reshape our understanding of that first, miraculous moment when everything began. The cosmos began in chaos, but it chose order. We have traveled from the faint microwave whisper of the Big Bang to the vast, silent voids between galaxies, all to answer a single, profound question. Why is everything so deeply the same? The answer lies in a flash of unimaginable violence, a growth spurt in the universe's first instant that stretched a subatomic seed into our entire observable reality. This inflationary moment did more than just solve the horizon problem. It ironed out the cosmos, forcing it into a state of flatness and thermal equilibrium that has persisted for 14 billion years. The uniform temperature of the cosmic background, the identical laws of physics in distant galaxies, the very flat geometry of space itself, these are not cosmic coincidences. They are the direct legacy of that initial explosive smoothing, a fundamental feature woven into the fabric of reality at its birth. We are left with a universe that is both intricately structured and profoundly uniform, a cosmic democracy where no place is more special than any other, all born from a single, unified moment. So we leave you with a question to ponder. What aspect of this cosmic sameness captures your imagination the most? Is it the synchronized temperature of disconnected realms, or the single set of rules that governs everything from your hands to the farthest star? Share your thoughts in the comments below, and if you enjoyed this journey through the deepest mysteries of space, please like, subscribe, and hit the notification bell for more explorations into the